Okay, this is Basic Calculus 1 lecture 20. So, if you remember, in a problem we have encountered for the computing maxima and minima, we had found out the critical point, and then we just referred to the picture of the function or the graph of the function to say that at that critical point there is a local maximum. At that point we did not have analytic tools to determine whether a critical point is a point of maximum or a point of minimum. So, today we will use the first derivative of the function to deduce whether a critical point is an extreme point, or if it is so, what kind of extreme point it is. Is it maximum or it is minimum locally? So, that idea is very easy. For example, if you have some curve, you have a maximum point somewhere at C, then you see that to the left of it the function is increasing and to the right of it the function is decreasing. So, you must know first how to use the information on the derivative at that point C to say whether it is increasing in a neighborhood of that C or it is decreasing in a neighborhood of C. Specifically, we will need something like on the left side it should be increasing, on the right side it is decreasing, or if it is a minimum point, then in the left side it should be decreasing and on the right side it should be increasing. So, we need to know something about increasing and decreasing nature of functions basing on this idea of the derivative. So, let us do that first. That is called monotonicity. So, suppose f is a function defined on an interval I, its domain is I and codomain is R, of course. So, now for this function we say that it is increasing on I. You could have taken a subset of that I, say j, and say that it is increasing on j. We are writing directly on I. Fx is increasing on I if what happens? For any 2 points s and t inside that interval I, if s is less than t, then you should have f of s to be less than f of t. So, t is to the right and f of t to the top of f of s. That is how you say it is climbing up or it is increasing. And similarly, we will say that f of x is decreasing on I if s is less than t, that is t is to the right, but you have f of s is larger than f of t. So, it is climbing down or it is decreasing. And if it is either increasing or decreasing, one of them, we would say that it is monotonic. So, it is monotonic on I if either it increases on I or it decreases on I. For example, suppose you take f of x equal to x square. It is defined on the whole of R. At 0 it is 0, but when it is negative, this x square it is positive, and when it is positive, x is positive, it is also positive. Okay, what happens when it is on the right side of 0, that is it is all non-negative numbers, then x square you would look something like this. So, it increases, and when you say that we choose x from minus infinity to 0, that is x is not positive, it is either negative or 0, then f of x square looks like this. So, it is decreasing. So, it is increases on 0 to infinity close 0 and decreases on minus infinity to 0. So, it is monotonic on minus infinity to 0, it is also monotonic on 0 to infinity, it is one of them increasing or decreasing. But on the whole of R, if you take that interval, it neither increases nor decreases on the whole of R. So, it is not monotonic on R, but it is monotonic on these two sub intervals. At one place it is decreasing, at another place it is increasing. So, our guiding principle will be a result for using the information on derivative to say whether it is increasing or decreasing. So, suppose we have a function which is continuous on the closed interval a b and differentiable on the open interval a b. Now, if f prime x is greater than 0 on the open interval a b, because there only it is defined, then f of x is increasing on the whole of a b. So, how come this a and b is coming? It is because of continuity is taking care, right, at a and at b. So, if f prime x is bigger than 0 on a b, it is positive, then f x is increasing. Of course, when it is positive, its tangent will be something like this. So, curve will be increasing. At any point, you see tangents will be this way. So, that is intuitively. So, this is what we will see. And if f prime x is less than 0 on a b, then f of x will be decreasing on closed interval a b. So, let us take say 1. How do we prove 1? Suppose s is less than t, both are in the closed interval a b. Now, we will use the mean value theorem. It satisfies the conditions of the mean value theorem. So, its conclusion is f t minus f of s, our t is to the right of s, equal to f prime c times t minus s. For some c, there exists a c inside the open interval s t, such that f prime c times s minus t will be equal to f t minus f s. Now, we will use the information that f prime x is greater than 0 on f b. So, in particular at c, it is positive. So, since this is positive and t minus s is positive, we get f t minus f s is positive. That is, f t is bigger than f of s. So, I think that is the end of the proof. It shows that f x is increasing on a b. Now, similarly, if you take the other one, f prime x is less than 0, again from the mean value theorem, you will see that f prime c is negative, this is positive. So, the right side is negative, therefore, f t is less than f of s and f is decreasing. So, this is easy, but there is another thing. If f prime x is continuous, we have not assumed continuity of f prime anywhere. In addition, if it is continuous, then it will help us in finding out the maxima and minima of the function. So, we will see soon. Let us take an example first for this illustrating this result. Suppose consider the function f of x equal to x cubed minus 12x plus 5. So, what we are asked is, you find the critical points of this and find out where the function is increasing, where the function is decreasing, and basing on that, if possible, find the maximum and minimum values of f of x and where do they occur. So, all these things have to be obtained, but first we have to find out critical points. Now, first of all, this f of x is defined everywhere on R. So, every point is an interior point and it is differentiable over R. So, critical points will be those where it is differentiable, where the derivative is 0. Okay. So, what do we do? Find out its derivative. It is 3x square minus 12, that is it. And to find the critical points, we equate this to 0 and compute where it can be 0. So, we find that at x equal to plus or minus 2, this f prime x can be 0. So, we have now minus 2 a critical point and 2 is also a critical point. Now, that divides the whole of R into 3 sub intervals, right. So, one is minus infinity to minus 2, another is minus 2 to 2, another is 2 to infinity. So, we are going to find out whether f prime has the same sign over all these intervals. If that is so, then it will be either decreasing or increasing on those intervals, leaving these 2 points, of course, critical points. Now, what happens? On minus infinity to minus 2, f prime x is greater than 0. Why? F prime x is equal to 3x square minus 12. So, once you take anything which is smaller than minus 2, its square will be bigger than 4. So, 3x square minus 12 will be positive. That is what we say, f prime x is positive on minus infinity to minus 2. So, that means f of x is increasing in this interval minus infinity to minus 2. Similarly, if you take f prime x, whether it is positive or negative inside the interval minus 2 to 2, you see that f prime of x equal to 3 into x minus 2 into x plus 2. So, inside the interval, if you check any x, one of them will be positive, one of them will be negative. X plus 2 will be positive, x minus 2 will be negative. Therefore, f prime x is always negative for every point x chosen between minus 2 to 2. Therefore, f x is decreasing on minus 2 to 2. So, that is clear. Now, let us consider the next interval. Suppose I choose x bigger than 2, x from 2 to infinity. Then x square will be again bigger than 4. So, 3x square minus 12 will be positive. F prime x is positive on 2 to infinity. Therefore, f x is increasing in this interval 2 to infinity. So, how does it happen? Let us look at the summary. It is increasing on minus infinity to minus 2. So, it is minus 2, 2, and it is increasing from minus 2 to 2. It will not happen there, of course, because f at minus 2 is 0, it may happen here downside. Then it is decreasing minus 2 to 2. So, will it look like? It will be something like this, decreasing, but it decreases to 0 again at 2, right. Then what happens? It is for the f. So, f is increasing on 2 to infinity, again it will be looking something like this. Okay, that is how it looks, increasing on minus infinity to minus 2, decreases on minus t to 2, and increases from 2 to infinity. So, that means it is increasing on minus infinity to minus 2, okay, and then it is decreasing from minus 2 to 2. So, at 0 there is a local maximum. It is a critical point, but since it is increasing and decreasing, that should be maximum, because definition of maximum, local maximum is on a neighborhood, left neighborhood it will be decreasing, increasing, and on the right neighborhood it should be decreasing. Then there is a local maximum. That is what happened at minus 2. Therefore, it has a local maximum at x equal to minus 2, and if you evaluate at minus 2, it is minus 8 plus 24 plus 5. So, that gives you value 21. So, f at minus 2 is 21. So, that means it is f prime though will be like this negative, but it will be something like it is increasing. So, somewhere it will go like this up to 21. That is how it looks. Okay. Then what about at 2? At 2 again, to the left of it is the interval minus 2 to 2. There it is decreasing, and to the right of it, it is increasing. So, there is a minimum value at x equal to 2, and if we substitute again x equal to 2, you would get it to be minus 11. So, from 21 at minus 2, from 21 it decreases to minus 12. Looks something like this, but not exactly. It is square, of course, it is cube. So, it comes like this. Then what happens? So, these are the two values, critical values are minus 2 and 2. At one place it has local maximum, which is at minus 2, and another place it has local minimum, which is x equal to 2. Now, if you compare the values, there is nothing to compare here, there is one maximum, one minimum, but among these it is local. So, one can be smaller, one can be bigger also, even if it is otherwise. Minimum can be bigger, local minimum can be bigger than the local maximum, because they are having at different places. But here what happens? It is f at minus 2 is 21, which is maximum. So, absolute maximum is 21, and comparing these two values, we say absolute minimum is minus 11, right. So, that settles finding out maxima and minima, and it is identify the intervals. So, the intervals are here where it is monotonic, and it has different behavior in the different intervals, and they are local maxima, they are also absolute maxima and absolute minima. So, this is how we are going to use the information on the derivatives, but we will make a shortcut again. Let us try that. So, what we have seen that f prime x, it is greater than 0. So, it increases, f is increases, and then since it is a local maximum, it is decreasing. So, f prime is less than 0 there, that is what we have found out. So, that means f prime is positive to the left of the critical point and negative to the right of the critical point. At the critical point it is 0. So, that is what we say, it is some sign change is happening in f prime x. So, let us see what does that mean. Suppose we have a function g from d to r and let c be an interior point of d. At the interior points only we are going to consider the critical points. We say that gx changes sign from minus to plus at x equal to c if there is a neighborhood of x. In the left neighborhood c minus delta to c, gx is less than 0, and in the right neighborhood c to c plus delta, gx is greater than 0. So, that is clear how, why do you say changes sign from minus to plus. On the left of it is minus, on the right of it is plus. So, you say that it is changing sign from minus to plus at x equal to c. Of course, at x equal to c it is 0, if g is continuous it has to be because of intermediate value theorem. Okay. We said that gx changes sign from plus to minus at x equal to c if the inequalities are changed. That is, in the left neighborhood c minus delta to c, we have gx greater than 0, and in the right neighborhood c to c plus delta, we have gx less than 0. Changes sign from positive to negative. So, that is what about g. We just defined what is the meaning of changes sign from, which is intuitively obvious. But this delta is not every delta, there exists some delta, there is a neighborhood in which this thing happens. Okay. So, gx changes sign from minus to plus means gx is negative on the interval, that is to the immediate left of c, and it is positive to the immediate right of c. Similarly, it changes sign from positive to negative means on the left of c it is positive, on the immediate right of c it is negative. That is its meaning. Okay. So, how we are going to use this information? Let us look at, say, f is a function given like this. Look at the picture. Then f prime equal to 0 as a point, say f prime at c3. Here what happens? F prime is less than 0 throughout this, but all that we need is a neighborhood c minus delta to c plus delta, where f prime is negative, on the right of it f prime is positive. So, that means f prime is changing sign from negative to positive at c. So, if that happens, look at point 1 above, f prime changes minus to plus at x equal to c, then f x has a local minimum. That is what we see from the picture. So, what are the conditions for this to be satisfied? Of course, all these analysis will be correct provided we have continuity, differentiability and so on. So, we should formulate that. Let f x be a continuous function on an interval I. Let us say c belongs to I be critical point of f x. Now, assume that f x is differentiable everywhere except possibly at c. If at c it is not differentiable, that is also a critical point, right. So, at least on I minus c it should be differentiable. Now, what happens? If f prime x changes sign from minus to plus, look at this c3, then f x has a local minimum at x equal to c. And if f prime x changes sign from plus to minus at c, then f x has a local maximum at x equal to c. For this, just look at the point c2. So, f prime is changing sign from positive to negative at x equal to c2. So, at c2 there is a local maximum. Now, if f prime x does not change sign at x equal to c, then f x has no local extremum at x equal to c. So, it is possible, let us look at c1, f prime is greater than 0 before it, f prime is bigger than 0, greater than 0 also after it. So, at that point there is no local extremum, fine, because otherwise on the right side at least should have been decreased, then it is maximum, but it is not. So, if it does not change sign at x equal to c, then it does not have a local extremum at that point. Similar thing happens for the other side when it is look at the point C5, f prime does not change sign there. To the left of this point C5 it is negative, to the right also it is negative. So, there is nothing. But something we can say about the endpoints which will come later. What happens here? On the endpoints you do not have the notion of one side neighborhood, only one side neighborhood is there, right. So, on the left side here, for example, at A there is no neighborhood which is relevant to the functions, the domain of the function, but to the right there is a neighborhood A to A plus delta. Similarly, at the right end point we have the left neighborhood, we do not have the right neighborhood. So, in this case we would say that there is a local minimum at x equal to A if f prime is positive after A, right, that means f is increasing after this. So, it becomes minimum. Similarly, at B we can say it is local minimum if it is f is decreasing, right. So, the other things can also happen, like at A for example the function comes like this. So, it will happen that f prime, this function will be decreasing here. So, f prime will be less than 0 at A, that is also possible. Similarly, at B also it is possible. So, this way, so f prime is positive there, right. So, it is increasing, then local maximum can happen there. So, for the endpoints we will consider only one sided neighborhoods whichever is relevant, that is what it says. Okay, so, basing on this left side and right side thing, we should formulate our conclusion about the local maximum, local minimum.